Hello, Calc students. This is Mr. Foster. We're talking about the chain rule boogie today. So this is another method for taking derivatives and is appropriate when you have a composite of functions. Different than when you have two functions being multiplied together. You've learned that you've got to use the product rule for that. We're talking about something different here, using the chain rule for a composite of a function or functions. All right, so the chain rule for derivatives, here's the rule that you would see in your textbook. Supposing f and g are both differentiable, when you want to take the derivative of the composite function f of g of x, not f times g of x, f of g of x, you need to do this. It's kind of color-coded on purpose. The first thing you need to do is take the derivative of the outside function. If I said, what's the outside function and the inside function? Well, the inside function is pretty easy to see. I would bet nickels to donuts that you'd say, I think the inside function is g of x, and you would be right. So the outside function is f. And so the first thing you need to do is take the derivative of f. In doing so, you leave g of x alone. You leave g of x alone. The second part of the chain rule is then you take the derivative and multiply the derivative of that inside function. So you're going to multiply by the derivative of the inside function. So when you get a function that is a composition of two functions or a composition of multiple functions, you'll see later, the chain rule is what you need to use. We'll get used to this. A few points of emphasis. Number one, you're going to use this rule when you have functions inside of other functions. I sometimes call that function f is pregnant with the function g. All right? I refer to the function g as the baby. And when we take the derivative, the first thing you do is take the derivative of f and don't disrupt the baby. Leave the baby alone. So that's what I mean when I'm talking about the inside function. Leave the inside function alone. The inside function will remain the same. The point of emphasis here, remember that your inside function, unchanged, goes inside the derivative of the outside function. The inside function, unchanged. The inside function goes unchanged in this process until the very end when you take the derivative of that inside function, what you're seeing here in yellow. Okay? So you'll get in a groove here and understand what's going on. We've got 4 examples coming. They kind of go from easy to more difficult, but nothing too crazy. Here, the directions for each of these is to find the derivatives of the following functions. The first function is f of x equals x cubed plus 4 to the raised to the 50th power. So I challenge you to find the inside function. What is the inside function? Well, the inside function is x cubed plus 4. It's some stuff being raised to the 50th power. That stuff is the inside function. There's the inside function, squiggly lined. So I take that stuff raised to the 50th power. The stuff raised to the 50th power has a derivative. If I take the derivative of that, I get 50 times that stuff. Don't disrupt the baby. Raised to the 49th power. Now it's time to take the derivative of that inside function. Go ahead and say it out loud. You can do it. Go ahead. Say the derivative of that squiggly line stuff. I agree with you. 3x squared is the derivative of the inside function. The only thing I do now is just reformat things. I go 3x squared times 50 to get my final answer here. 150x squared times quantity x cubed plus 4 raised to the 49th power is the way you would see your answer on a Foster Wheeler AP exam or in the back of your textbook, etc. There's number 1. Here's number 2. G of x. is the square root of 4x squared plus 3x plus 7. So as I say, things become a little more difficult here, but not terribly more difficult. So the inside function is the stuff inside the hood, the stuff in the hood. All right. And what I want to do is I want to rewrite this so it's in exponent form. So my first step is to do a rewrite and rewrite this as 4x squared plus 3x plus 7 all raised to the 1/2 power. This is going to allow me to do the chain rule in a little easier fashion. Okay, so I got some stuff raised to the 1/2 power. That's the first thing you have to take the derivative of. The outside function. So to find g prime of x, the first thing I do is take the derivative of that stuff raised to the 1/2 power. That's going to have derivative 1/2 times the unchanged stuff. Don't disrupt the baby. Raised to the negative 1/2 power. Multiplied by the derivative of the inside function. Can you take the derivative of the inside function? Do you know what I'm going to write down next? 8x plus 3. I agree with. Here is the final answer to number 2. So I'm taking the derivative of the outside function without disrupting the inside function, then simply multiply that by the derivative of the inside function. Again, chain rule used for when you have scenarios of composition functions. Here comes number 3. This time I have e raised to the 5x. E raised to the 5x. So here's a warning for you. A lot of students make this mistake. I know that when I take the derivative of e to the x, I get e to the x. Mrs. Wheeler's video told me this. My exponential video said, hey, Chachi, when you take the derivative of e to the x, you get e to the x. So a lot of calc students are under the impression that when they take the derivative of e to the 5x, they would get e to the 5x. This is untrue. The derivative of e to the 5x is not e to the 5x. We've got to take the chain rule here. We have e raised to some stuff. Yeah, the some stuff. The 5x is the inside function here. These are not equal to one another. Okay, so what I'm going to do here is I take e to the 5x. So that's the outside function, e to the 5x, and the inside function has derivative 5. Final answer, 5e to the 5x. Okay? I'm not ecstatic about what I squigglied and squared here. Truth be known, I should have squigglied the 5x and put a square around the e to the 5x. Anyways, if you realize the inside function is that 5x, you take the derivative of the outside function, you get e to the 5x. And then make sure you multiply by the derivative of the inside function, which is 5. So don't make that common error that a lot of calc students make. They're under the misconception, since the derivative of e to the x is e to the x, they leapfrog and believe the derivative of e to the 5x is e to the 5x. That is not true. You're seeing here the derivative of e to the 5x is in fact 5e to the 5x because you're using the chain rule. Last example. Again, a little more difficult. It's got to occur to you to do a rewrite step here in order to see clearly the inside function. So if I have f of x equal to 1 all over x squared plus 4x cubed, the rewrite is going to make this clear for me in order to use the chain rule. The rewrite is x squared plus 4x cubed, all raised to the negative first power. That stuff in the denominator I can bring up to the numerator as long as I write it with an opposite exponent. So now I clearly have an inside function of x squared plus 4x cubed. And to take the derivative, I think about that inside function. I just replace it with some stuff. I got some stuff raised to the negative first power. How would you take the derivative of some stuff raised to the negative first power? Well, some stuff raised to the negative first power, if I took the derivative of that, I'd take that negative 1 exponent and multiply it by the understood coefficient in front, which is 1. I would keep the inside function unchanged and subtract 1 from the exponent. The inside function is unchanged in this portion of the chain rule. Oh, so I'm done now? No, you still have to take and multiply the derivative of the inside function, which is a simple power rule scenario. The derivative of the inside function, say it to yourself, go ahead. The derivative of the inside function is 2x plus 12x squared. There's the answer for number 4. So in each of these cases, you can see all 4 problems are compositions of functions, like I have a function within a function. And to take the derivative of these scenarios, you have to take the derivative of the outside function. In doing so, leave the inside function unchanged, and then multiply whatever you now have by the derivative of the inside function. That'll give you the answer to your chain rule. Sometimes it just requires a little simplification at the end so that your answer matches that in a multiple choice scenario or an answer in the back of your textbook. Okay? There's the chain rule in a nutshell. Know it, learn it, love it, live it. Good luck.